The James Webb Space Telescope is upsetting the apple cart. All of a sudden, we realize that we may have to rewrite all the textbooks about the beginning of the universe. In their quest to understand the first stars and galaxies that lit up the cosmos, astronomers are still in the dark but getting closer to enlightenment one discovery at a time. That's the incredible, inescapable conclusion from unprecedented discoveries by the James Webb Space Telescope, or JWST, the $10 billion time machine that just officially closed its first year of observations. Designed to glimpse the faint infrared glow of the universe's earliest luminous objects, Webb's vision reached back into the first few 100 million years after the Big Bang, allowing it to obtain more and better data about newborn galaxies than any other facility yet built. But its haul of galactic baby pictures has proved more bountiful than most researchers dared to dream. Simply put, candidate galaxies in the early universe are popping up in numbers that defy predictions, with dozens found so far. That makes scientists freak out, as Charlotte Mason, an astrophysicist at the University of Copenhagen, said, "We really weren't expecting this." In the weeks and months following JWST's findings of surprisingly mature early galaxies, theorists and observers scrambled to explain them. Could the bevy of anomalous dim and bright early galaxies be illusory, perhaps because of flaws in analyses of the telescope's initial observations? If genuine, could they somehow be explained by standard cosmological models? Or just maybe were they the first hints that the universe is more strange and complex than even our boldest theories had ever supposed, and the Big Bang Theory was wrong? Join us today as we dig deep into how the James Webb Space Telescope broke the universe. Let's get to the point. To understand the dilemma, let's go back to when the universe was believed to have been formed. After the Big Bang, the infant universe began cooling off. Within a few million years, the roiling plasma that filled space settled down, and electrons, protons, and neutrons combined into atoms, mostly neutral hydrogen. Things were quiet and dark for a period of uncertain duration known as the Cosmic Dark Ages. Then something happened. Most of the material that flew apart after the Big Bang is made of something we can't see, called dark matter. It has exerted a powerful influence over the cosmos, especially at first. In the standard picture, cold dark matter, a term that means invisible, slow-moving particles, was flung about the cosmos indiscriminately. In some areas, its distribution was denser, and in these regions it began collapsing into clumps. Visible matter, meaning atoms, clustered around the clumps of dark matter. As the atoms cooled off as well, they eventually condensed and the first stars were born. These new sources of radiation recharged the neutral hydrogen that filled the universe during the so-called epoch of reionization. Through gravity, larger and more complex structures grew, building a vast cosmic web of galaxies. Meanwhile, everything kept flying apart. The universe is expanding rapidly. The astronomer Edwin Hubble figured out in the 1920s that the universe is expanding, and in the late 1990s, his namesake, the Hubble Space Telescope, found evidence that the expansion is accelerating. Think of the universe as a loaf of raisin bread. It starts as a mixture of flour and water, yeast, and raisins. When you combine these ingredients, the yeast begins to respond, firing, and the loaf begins to rise. The raisins within it stand in for galaxies, stretching further apart from one another as the loaf expands. The Hubble telescope saw that the loaf is rising even faster. The raisins are flying apart at a rate that defies their gravitational attraction. This acceleration appears to be driven by the repulsive energy of space itself, so-called dark energy. Plugging values for cold dark matter, regular matter, and radiation into the equations of Albert Einstein's general theory of relativity matches almost all observations of the cosmos. One way to test this picture is by looking at very distant galaxies, equivalent to looking back in time to the first few 100 million years after the tremendous clap that started it all. The cosmos was simpler then, its evolution easier to compare against predictions. Astronomers first tried to see the earliest structures of the universe using the Hubble telescope. In 1995, over 10 days, Hubble captured 342 exposures of an empty-looking patch of space in the Big Dipper. Astronomers were astonished by the abundance hiding in the inky dark. Hubble could see thousands of galaxies at different distances and stages of development, stretching back to much earlier times than anyone predicted. Hubble would go on to find some exceedingly distant galaxies. In 2016, astronomers found its most distant one called GNZ11, a faint smudge that they dated to about 400 million years after the Big Bang. Ever launched from Earth, the JWST was built to revolutionize our understanding of the universe. Stationed 1.5 million kilometers away from earthly interference and chilled close to absolute zero by its tennis court-sized sunshade, the telescope carries a giant segmented mirror and exquisitely sensitive instruments that were designed to uncover details of cosmic dawn never before observed. And that promise was kept as the first discoveries were obtained within just weeks after JWST's full operation began. JWST's early discoveries were beyond astronomers' wildest dreams. It has seen galaxies breathtakingly close to the dawn of time, probed the atmospheres of exoplanets in unprecedented detail, and provided stunning new views of worlds in our solar system. But it's just getting started. As Webb's vision reaches back into the first few 100 million years after the Big Bang, allowing it to obtain more and better data about newborn galaxies than any other facility yet built, at stake is nothing less than our very understanding of how the orderly universe we know emerged from primordial chaos. Webb's early revelations could rewrite the opening chapters of cosmic history, which concern not only distant epochs and faraway galaxies, but also our own existence here in the familiar Milky Way. As JWST scientist Mark McCaffrian, a senior advisor for space and exploration at the European Space Agency, said, "You build these machines not to confirm the paradigm but to break it. You just don't know how they will break it." Researchers use a version of the Doppler effect to gauge the distances of objects. This is similar to figuring out the location of an ambulance based on a siren. The siren sounds higher in pitch as it approaches and then lower as it recedes. The farther away a galaxy is, the faster it moves away from us, and so its light stretches to longer wavelengths and appears redder. The magnitude of this redshift is expressed as z, where a given value of z tells you how long an object's light must have traveled to reach us. One of the first papers on JWST data came from Natu, the MIT astronomer, and his colleagues, whose search algorithm flagged a galaxy that seemed inexplicably bright and unaccountably distant. Natu dubbed it Glass Z13, indicating its apparent distance at a redshift of 13, further away than anything seen before. The galaxy's redshift was later revised down to 12.4, and it was renamed Glass Z12. Other astronomers working on various sets of JWST observations were reporting red shift values from 11 to 20, including one galaxy called Sears 1749, whose light appears to have left 13.7 billion years ago, just 220 million years after the Big Bang, barely a blink after the beginning of cosmic time itself. The ages of some of the alleged high redshift galaxies have been reconsidered. Some were demoted to later stages of cosmic evolution because of the updated telescope calibrations. Sears 1749, for example, is found in a region of the sky containing a cluster of galaxies whose light was emitted 12.4 billion years ago, and Natu says it's possible the galaxy is part of that cluster. It is also possible that something similar was seen closer to home. While astronomers are working to verify many JWST observations, they have confirmed others. For example, Natu's Glass Z12, and even more importantly, the telescope's most distant confirmed galaxy to date, JAD's GSZ 13 SER, which was announced in December and whose starlight was emitted 13.3 billion years ago. It does hint that something may be missing. If so, the additional ingredient must be compatible with other existing observations, including detailed maps of radiation left over from the Big Bang and studies of galaxies from later epochs. One possibility is that the earliest galaxies were simply more efficient at forming stars than those seen today. Some researchers have proposed that JWST's bright early galaxies contained gargantuan supermassive stars composed of pure hydrogen and helium, whose lives and deaths would have been distinctly different from today's stars. Another possibility is that dark matter did something different in the early universe. Some theorists have proposed that the earliest galaxies were more efficient at forming stars than those seen today. Some researchers have proposed that JWST's bright early galaxies contained gargantuan supermassive stars composed of pure hydrogen and helium, whose lives and deaths would have been distinctly different from today's stars. Another possibility is that dark matter did something different in the early universe. Some theorists have proposed that the earliest galaxies were more efficient at forming stars than those seen today. Some researchers have proposed that JWST's bright early galaxies contained gargantuan supermassive stars composed of pure hydrogen and helium, whose lives and deaths would have been distinctly different from today's stars. Another possibility is that dark matter did something different in the early universe. Some theorists have proposed that JWST's bright early galaxies contained gargantuan supermassive stars composed of pure hydrogen and helium, whose lives and deaths would have been distinctly different from today's stars. Another possibility is that dark matter did something different in the early universe. Some theorists have proposed that the earliest galaxies were more efficient at forming stars than those seen today. Some researchers have proposed that JWST's bright early galaxies contained gargantuan supermassive stars composed of pure hydrogen and helium, whose lives and deaths would have been distinctly different from today's stars. Another possibility is that dark matter did something different in the early universe. Some theorists have proposed that JWST's bright early galaxies contained gargantuan supermassive stars composed of pure hydrogen and helium, whose lives and deaths would have been distinctly different from today's stars. Another possibility is that dark matter did something different in the early universe. Some theorists have proposed that JWST's bright early galaxies contained gargantuan supermassive stars composed of pure hydrogen and helium, whose lives and deaths would have been distinctly different from today's stars. Another possibility is that dark matter did something different in the early universe. Some theorists have proposed that JWST's bright early galaxies contained gargantuan supermassive stars composed of pure hydrogen and helium, whose lives and deaths would have been distinctly different from today's stars. Another possibility is that dark matter did something different in the early universe. Some theorists have proposed that JWST's bright early galaxies contained gargantuan supermassive stars composed of pure hydrogen and helium, whose lives and deaths would have been distinctly different from today's stars.